This presentation is delivered by the Stanford Center for Professional Development.
Okay, let me remind you where we finished up last time. We took an important first step in understanding the analysis and undertaking the analysis of periodic phenomena and trying to represent general periodic phenomena by the sum of much simpler periodic phenomena. That is complex exponentials. So think in terms of sines and cosines. All right. So last time, I say we took the first step in analyzing general periodic phenomena via the sum, so a simple combination, linear combination of simple building blocks, simple periodic phenomena. So let me remind you what we did, because it's very important that you realize what we did and what we didn't do. We said, suppose that you can write a periodic signal in a certain form, what has to happen? So we start off by saying f of t is a given periodic function, periodic signal, function signal, same thing. And just to be definite, we took it to have period 1, all right? And the question is, can it be represented in terms of others, and suppose it can be represented in terms of other simple signals of period 1, namely the complex exponentials. So suppose we can write f of t as a sum, say something like this, k from minus n to n, c sub k, e to the 2 pi I, kt. There was a question, by the way, somebody sent me an email about why the sum is symmetric, and so why does it go from minus n to n. And we talked a little bit about this last time. This is also discussed a little bit more in the notes. You can think of this in terms of sines and cosines, all right? And the idea is that if you have a real signal, the coefficients, I mentioned this last time, but it bears repeating, the coefficients satisfy an important symmetry relationship. They're complex numbers. The c sub minus k is equal to c sub k bar, and because of that, the positive frequencies combine with the negative frequencies, the positive terms combine with the negative terms to give you a real part, so give you essentially a sum of cosines, okay, or sum of sines and cosines because the values are complex. And it's a symmetric sum. Instead of going from 1 to n or from 0 to n, if you use complex exponentials, it goes from minus n to n. The proof of the helpfulness of this representation will just become apparent as we use it, all right? As I said before, the algebraic work in the analysis is just made incomparably easier by using complex exponentials than real sines and cosines. So just the calculations become that much easier. All right, so once again, suppose we can do this, then what we found is the coefficients had to be given by a certain formula. So then the coefficients are given by c sub k is the integral from 0 to 1 e to the minus 2 pi I kt times f of t dt. All right? There's an explicit formula for the coefficients. And in principle, that's known. All right? If you know the function, then you can carry out the integration in principle. And I want to remind you that this formula, there were two parts of deriving that formula. There was sort of an algebraic part where we just try to isolate the kth coefficient, and that's a certain way. But then the analytic part invoked a little calculus, where to solve for the coefficient I had to integrate, and this depended on a very important relationship of the complex exponentials. This, I'll write it over here. I'll write it here. The integral from, I'll write it over here. The integral from 0 to 1 e to the, say, 2 pi I nt e to the 2 pi minus 2 pi I mt dt. So that's integral from 0 to 1. If I combine the two, e to the 2 pi I n minus m t dt, that's either 1 if m is equal to n. So in that case, I'm just integrating e to the 0. I'm just integrating 1. Or it's equal to 0 if m is different from n. All right? Fundamental relationship. And we'll see that making its triumphant return a little later on. All right. Now, that's fine. And that was a very important first step, but it was only the first step. The second step is to turn the question around. All right? The first step said, suppose we can write the function in this form, then the coefficients have to be given by this formula. The second step is to turn that around and ask the following. When is that really possible? So I want to turn this around. So again, you're given f of t, periodic of period 1. All right? I know what the answer has to be. All right? In the sense, I know what the coefficients have to be. They have to be given by this. So I'm going to define them. All right? Define. And I want to use a different notation. I want to introduce a different notation that's quite standard in the subject. Define f hat of k to be this integral, the integral from 0 to 1 of e to the minus 2 pi I kt f of t dt. So again, in principle, you can compute this. All right? You're given f. You can carry out the integration of f against this complex exponential. And it's often denoted by f hat k, and this is called the k Fourier coefficient. Of f. Let me just say k Fourier coefficient. All right, so it depends on f. And in fact, it can be viewed as a transform of f, although we won't use that terminology. Well, I won't stress that terminology quite so much now because it'll become much more useful when we talk about the Fourier transform. This is not the Fourier transform. This is the Fourier coefficient. So it's a transform of f, but evaluated on the integers. For each k, I have a corresponding number, f hat of k, given by this integral. And the question is, can we write the function, can we synthesize the function in terms of its Fourier coefficients? Can we write f of t is the sum from k equals minus n to n f hat of k e to the 2 pi I kt for some n? Is there some sum of these things that will allow us to express the given periodic function in terms of these simple building blocks? That's the question. I say I know what the answer has to be. If we can do it, the answer has to be given. Such an expression has to involve this. That's what I talked about last time. The question is, does it really work? If it does, if a statement like this is true, you have to believe that it gives you incredible power because, again, a general periodic function can be decomposed in this way into very simple terms. Analyzing a very complex system of periodic inputs, periodic outputs might very well be might be possible to do by analyzing what the system does to the relatively simple inputs and outputs given by the complex exponentials. All right? So if so, we can analyze complex systems simple building blocks. Simple building blocks. Not a great sentence here, but you get what I mean. Simple components, simple building blocks. I'd like another try at that sentence, but I think I'd just rather leave it there. All right? Okay. Now, this method is only going to be really helpful if it's fairly general. And that's always been the question I've raised a couple times. How general really is this? How general can we expect this to be if it works? All right, is it worth putting the time and effort into even addressing this question if it's only going to work in a few specialized cases, you know, that somehow we could handle on an ad hoc basis when they came up? Well, let me give you a little warning here. All right, let me show you the kind of things. Not to be negative about it, but let me show you how high the stakes are. All right, this is a very high stakes question. And let me do that by a couple of examples. All right, examples that are natural enough and can come up very easily in applications. Let's look at some examples. Of some of the kind of signals that could come up. For example, you could take a signal that looks like this. All right, I'll draw it over here. I'll just draw the graph. something that looks like this. It could model a switch that's periodically on or off, 0 or 1. The current is flowing or it's not flowing. So something like it's 1 for half a second and then 0 for half a second. All right? That's the basic period. And then it repeats. So 1 down to 0, 1 half. And then it repeats. Then it goes up, then it's on, then it's off. Then it's on, then it's off, and so on and so on. Okay? So 1, 3 halves, 2, and so on and so on. All right? That's a function of period. That's a periodic function of period. And it repeats also for the negative numbers. So that's a periodic function of period 1. All right? So switch. On for half a second, off for half a second. And it repeats. All right, can we expect to write, let's call this f of t, right? There's the graph, and I can write down a formula for it. Can we write f in the form? I can compute the coefficients. I won't do it, but in fact, the coefficients are calculated in the notes. All right? You can carry out the integration. It's not a complicated integral to carry out. You're just integrating the function 1 over the interval from 0 to a half. That's all of the function times a complex exponential. So you can compute easily f hat of k. F hat of k would be, in this case, the integral from 0 to a half. Let's say I won't carry it out, of e to the minus 2 pi I kt times 1 dt. All right, it's 1 on the interval from 0 to a half. It's 0 on the interval from 1 half to 1. You only compute it on the interval on one period, on the interval from 1 half to 0 to 1 half, and that's an easy integral to figure out. Can we write f of t is sum from k equals minus n to n f hat of k e to the 2 pi I kt? That's the question. And the answer is no. Or at least not for a finite, not with a finite sum. So I hate to build up all this drama asking this fundamental question only to answer it no for a relatively simple example. So the answer is no. Not for a finite sum. Why? Because the complex exponentials, they're just sines and cosines. All right? They're continuous. And the sum of a finite number of continuous functions is continuous. It can't possibly represent a discontinuous phenomenon. You can't represent a discontinuous phenomena by a continuous phenomenon. All right? You learned that theorem back in calculus. You know, somebody said, some jerk of a math teacher probably said something like, and the sum of two continuous functions, of course, is continuous. And you said, yeah, right, okay, fine. All right, and what's the point? Well, here's the point right now for the first time. This limits what you can do. This limits what you might want to do. You can't represent a discontinuous function by the sum of a finite number of continuous functions. Bad luck. All right? Well, what if the function is continuous at least? All right? But maybe has a corner. So let's look at a second example. Let's say a triangle wave. Something looks like this. Up, down, up, down, up, down, and so on. Say on an interval from 0 to 1. So it's periodic of period 1. And again, the pattern repeats along the negative axis also, or for negative values of t. So again, we can easily compute the Fourier coefficients. That's not a problem. They exist. It's not a problem to carry out the integration. And again, that's done. I think it's worked out in the notes explicitly. And if not, it's easy enough to do. I will not do it in public. Again, you can compute the Fourier coefficients. Has to be integrated in two pieces. Has to be integrated, the integral from 0 to a half of the function t times the complex exponential, plus the integral from 1 half to 1 of the function, whatever this is, on the corresponding interval, on the interval times the other, times the complex exponential. But you can do it, all right? It requires a little bit of work, but it's not hard. You can do it. Can we write, I'll call this f of t again. My generic function is always called f of t. Can we write, again, the corresponding sum? Sum k equals minus n to n e to the f hat of k e to the 2 pi I kt. And again, the answer is no. Not for a finite sum. Why? Well, because as your jerk of a calculus teacher probably told you, if your two functions are differentiable, then the sum of two functions is differentiable. And you said, fine, fine, whatever. And it didn't seem to matter at the time, but now it matters because this function is not differentiable. It has a corner, all right? But the complex exponentials are just sines and cosines. They are differentiable. Their sum is differentiable. You can't represent a non-differentiable function as a finite sum of differentiable functions. It won't work. You just can't do it. The right-hand side is differentiable. The left-hand side is not differentiable. Okay? Now, we could go on like this with more and more bad news. All right? That is, if there is a discontinuity so here there's a discontinuity in the first derivative, all right? There's a corner here. We could draw examples. It would look smoother, but we could draw examples where there's discontinuity in the second derivative. Or maybe the first and second derivatives are fine, but there's a discontinuity in the third derivative, and so on and so on. If there is any lack of smoothness, if there is any corner, no matter how smooth that corner looks, if there's some discontinuity in some high derivative, you're screwed, to use a technical term. All right? Any discontinuity in any derivative precludes writing f of t is this sum from k equals minus n to n of f hat of k e to the 2 pi I k t for a finite sum, because these functions are infinitely differentiable. These functions are as smooth as they can be. They're sines and cosines. And you can't take a sum of those sines and cosines and put them together and get something that's not infinitely differentiable. All right? So this great idea, we might as well quit now or take the rest of the quarter off, because it doesn't look very general at all. I mean, the kind of signals you come up against may have jumps, may have corners, may have discontinuities, whatever. All right, maybe we want to make an approximation that they're as smooth as can be, and then we can use this. And that's an argument, but, you know, it's getting away from what we really hope to accomplish here. Let me, before I go any further, say that there's a maxim lurking here that's important. All right? That is, if we can't represent it as a finite sum, then we have to turn to infinite sums, or at least larger and larger finite sums. Sums of more and more terms. And the maximum that's lurking here, I'll say it now, and then we'll go back to the general discussion, is that it takes high frequencies to make sharp corners, or any corners for that matter. Maxim is it takes high frequencies to make sharp corners. Or really any kind, it sounds better if you say it like this, but really any kind of corner. All right? Any time there's some kind of discontinuity in some high derivative, that means that you're going to have trouble representing that phenomenon as a finite sum. You're going to have to take n larger and larger to try to represent it more and more accurately, and it takes more and more terms, it takes higher and higher frequencies to make that bend. Right? Even in very high, even for a relatively high degree of smoothness. All right. Now, by the way, you may think again that this is an artificial maxim. That is, you know, real signals don't have sharp corners, but that's not true. I mean, all the time and later when we talk about filtering, producing sharp corners is often a very important part of, as sharp as you can, actually, is an important part of signal processing. Sometimes you want to take a signal and cut off after a certain point. Either cut it off in time or cut it off in frequency. Some of you, I'm sure, have had some experience with this. All right, so you want to, sometimes your signal starts out pretty smooth, but for other reasons you want to make it somehow less smooth. You want to cut things off. And cutting things off can introduce high frequencies in trying to represent the signal that is something else that has to be dealt with. All right, so there's some very tricky and very practical questions that go along with this maxim. All right, now, like I say, at this point you say, well, you know, what's happened to this grand general program that you've been announcing? If it's not going to work, I mean, if I can't consider finite sums to represent all but the most specialized phenomena, if there's some slight discontinuity in there at any level of smoothness, then what good is any of this? And the comeback to that is we have to consider infinite sums. All right? To represent the general periodic phenomena, periodic signals, we have to consider infinite sums. All right, that's a mathematical point. As a practical matter, of course, you can't sum up an infinite series. You can only sum up an approximation. But if you want to know, if you want to have some confidence in what you're doing, and if you want to know what errors you might have to analyze, the first thing you have to do is realize that you have to expand your purview from finite sums to infinite sums. So to represent more general periodic phenomena, we must consider infinite sums of the form, say, from minus infinity to infinity, f hat of k, e to the 2 pi I, kt. It may be that not all these coefficients are non-zero. Some of them may be 0 and so on. But for sure, if the function has any sort of discontinuity at any level of derivatives, then these coefficients are going to go out. They're going to be non-zero after a certain point. Or rather, they're going to go off to infinity. You're going to have non-zero coefficients as far as you go out. All right. Any non-smooth phenomenon, signal, will generate infinitely many, not just a finitely many, but infinitely many Fourier coefficients. All right? The only way you could possibly have a finite Fourier series is if the function you start out with were infinitely smooth. All right, now, that's a problem. All right? This is why I say the stakes are high here, because if you're going to deal with an infinite sum mathematically, and even for applications, you have to talk about issues of convergence. All right, how accurate is this going to be? If I cut it off after a finite number of terms, how accurate is it going to be? All right, if the series is converging, and I cut it off after a finite number of terms, maybe I have a certain amount of confidence that I'm getting a pretty good approximation to my function. All right, but if the series is not converging, and I still try to cut it off after a finite number of terms, what confidence do I have that I'm taking a reasonable approximation to the signal that I really want? So you have to deal with issues of convergence. You are forced to, if you want this theory to apply at all generally. Okay? And again, not just for mathematical reasons, but also for practical reasons. Now, that's hard, all right? There are a lot of very hard questions here. And we're not going to go into the mathematical analysis of all of them. I do want to give you a big picture. I want to give you some good news, and some hard news, but ultimately pretty good news, about how this is dealt with, because it has all been sorted out. But it took generations of mathematicians and scientists and engineers working on this to finally resolve all these issues. Why is this so? I mean, talking about convergence of series is hard anyway. It's particularly hard in cases like this, because the terms are alternating, or they're oscillating, all right? The complex exponential, again, think in terms of sines and cosines, all right? If I split this up into its real and imaginary parts, sometimes the cosine is positive, sometimes the cosine is negative, sometimes the sine is positive, sometimes the sine is negative. So you have positive terms and negative terms, and adding infinitely many of them up, all right? So convergence for an infinite sum like this has to depend on some sort of cancellations that are going on. There has to be some sort of conspiracy that's making this series converge for a given value of t, all right? You need a conspiracy of cancellations. How about that? Cancellations. To make such a series converge. Because of the oscillation. All right, and that's hard to study. That can be hard to study in a given case. So I just want you to be aware of this, that the stakes are high and the issues are real. Now, here's what I want to do. I want to talk about the situation. I want to give you a number of statements, theorems, that cover what the story is here. And again, we're not going to go through the proofs of these things. It's not so crucial for us, the mathematical details. A lot of them are covered in the notes, not all of them, however, and I'll say a little bit more about that as well. But I do want you to be aware of where the hard parts are and what the answers are. All right. So what I want to do is I want to summarize. I want to have a summary of the main results. That is, the convergence when the function is continuous, which happens often enough that you want to know. Or let me say smooth. It has to be an infinite series if it's not infinitely smooth. All right? The convergence, or what passes for convergence, when you have certain discontinuities. And here, there's a nice and helpful statement about when you have a simple discontinuity of a jump, when you have a jump discontinuity. All right. These two cases are actually relatively straightforward. It's easy to remember, and it's easy to have a certain amount of confidence in what the results are. Again, although we won't prove it for it. I won't prove it. I won't go through the proofs. And finally, the convergence issues in general. And they involve some really quite deep changes in the perspective that you have to adopt toward this circle of problems. Convergence in general. All right, you actually do have quite a broad general statement that covers all situations, pretty much all situations that come up reasonably in practice. But the notion of convergence is a little bit different, and the mathematics involved in here also it took a long time to sort out. All right, so this really involves this involves a fundamental change of perspective. As I said, I'm not going to do the details, but I at least want to say some of the words, and I'll tell you why. Because it has become so pervasive. That is, it's become so the framework for studying convergence in general, even as it applies maybe to these simpler situations, has become so standard that you will see this in all the literature. All right, you'll see in the engineering literature, you know, the terms that I'm going to use: orthogonality, mean square convergence, L2, things like that. I'll say all those words and I'll tell you what they mean. But it's become absolutely the way of talking about these things. And if you look at modern treatments of signal processing, and I'm thinking in particular here of wavelet analysis, which has become very popular in recent years, you'll hear about orthonormal bases for so-and-so, and distinguished from the complex exponentials as orthonormal bases. You'll hear all the terminology that goes along with this point of view. So I think at least I want you to come away from this with some understanding and familiarity with the terminology that goes along with it. All right, now that's all I want to. I really want to. That's as far as I want to go with it. But even that, I hope, is going to be helpful for you. All right, so let me look at these cases, because these cases are pretty straightforward and they're good to know. Convergence when the signal is continuous. Yes, good news, it converges. All right, so that is, continuous case. All right, so again, you can form the Fourier series. All right. You have that the series sum k equals minus infinity to infinity f hat of k e to the 2 pi I kt converges for each t to the value f of t. Pointwise. That means if you plug in a value of t into this sum and add it all up, then you have a series of constants, and what will it add up to? It will add up to the value of the function f of t. So that's good. All right, if the function is continuous, then you know the series is going to converge, and it's going to give you the right value. All right, good. Not so easy to prove. All right, it takes a little work to prove that, and again, that's sort of sketched out in the notes. All right, not all the details, but a number of them. At least you can see the broad outlines. And you will find this discussed in various levels of abstraction in most, certainly mathematical books on Fourier analysis, Fourier series. All right, but that's what to keep in mind there. So the continuous case is good. We call this point-wise convergence again because you plug in a value of t, a point in time, add up the series, which is then a sum of constants, and you're guaranteed that the sum will converge to the function f of t. In the case the function is smooth, actually you get a little bit more. If the function is differentiable, the smooth case so that's if you have various degrees of differentiability. If it has one derivative, if it has two derivatives, and then there's the question about are the derivatives continuous and so on. So I don't want to split hairs on this. And again, there's a fairly precise statement that's given in the notes. But it says this. So if it's smooth, then in particular it's continuous, so you know the series converges. So again, the series converges. The series, the Fourier series, k going from minus infinity to infinity, f hat of k, e to the 2 pi I kt, converges to f of t. That's the same as in the continuous case, but there's actually more to it than this that, again, can be helpful sometimes if you're trying to estimate errors. You actually get what's called uniform convergence. And what that means, the way you should think about this is, for different values of t, you can control the rate at which the series converges. Same rate for different values of t. So again, without trying to make it, I can make this precise, but I don't want to because it requires too much notation. So you can, i.e., think of it this way: you can control, or you can estimate the rate of convergence, how fast the series is converging at different values of t. Values of t depending on the degree of smoothness. What this often means is you get estimates on the size of the coefficients, you get estimates on the difference between the function and a finite approximation, a finite version of the series, depending on the smoothness. All right? The smoother the function is, the faster it converges. That's one way of looking at it. And again, without giving a technical definition of it. Yeah. Well, what this means is, what the uniform convergence means, roughly, and again, what I don't want to write a lot of epsilons and n's and things like that, is that if this is the function, all right, it's periodic, so the pattern repeats. Then what I mean by uniform convergence is that if you look at a finite approximation, so if you look at a finite version of the sum, just going from minus n to n, then that will track. So this is f of t. All right, that's the original function. Then and the approximation does something like, it tracks the function along the way. This is a finite sum. All right, you can estimate uniformly over the interval how far the approximation is from the function. All right, so instead of just saying at a particular point the series is converging, all right. So again, if I fix a particular point here, then the value of the approximation is approaching the value of the function. That's fine. That's what happens for the continuous case. For the smooth case, you can say more than that. You can say uniformly how close the approximation is to the function over the entire interval, overall from 0 to 1. All right, and you can give an estimate for that. All right, that's what the smoothness gives for you. All right, and again, you can write that down precisely, but I'm not going to do that. There is actually a statement of this theorem that's given in the notes, if you're interested. And it's interesting. I mean, it can have some practical implications because you're never going to work with an infinite series in practice. You're always going to work with a finite approximation. So the question is, can you estimate the error? Can you give, if you're called upon, can you give some reasonable estimate for how far off you are, not just at a point, but uniformly over the interval where you're interested in making the approximation? So it can come up. So you have uniform estimate of the closeness. Okay. All right, so that's the differentiable, that's the continuous case and the smooth case. So that's good news, all right? That's good news. That's nice. If the function is smooth, if the function is continuous, the series are converging. If the function is smooth, the series is converging and it actually sort of stays uniformly close to the given function. Now I want to jump back actually to the discontinuous case because there is one situation that comes up that often enough in practice that is useful to know about. And that's when you have a jump discontinuity. And again, I'm not going to prove this, but I think you should be aware of it. And there's actually going to be some problems that use it, or a problem that uses it. So if you have a jump discontinuity, functions can fail to be continuous in a lot of different ways. The simplest way a function can fail to be continuous if it has a jump discontinuity, like the first example that I showed. So the example of a switch where it's on then off. All right, something like this. All right, where the signal jumps down or up. Okay. So e.g. And there, the theorem is that if T naught is a point of jump discontinuity, this is a really cool result, actually. Then the converges, then the sum minus infinity to infinity e to the minus, or maybe I'll put it, well, yeah, I'll put it like this. Minus 2 pi I kt, sorry. F hat of k, the Fourier series, F hat of k e to the 2 pi I kt, does converge at t naught. It converges at the jump discontinuity, but the function doesn't really have a value at t naught because it jumps. But it converges actually to the average value. All right, it converges to the point in the middle of the jump. To the average of the jump, i.e. to 1/2, let me write it like this, 1/2 f of t naught, this is the usual way it's written, f of t naught plus f of t naught minus. All right? So what I mean by that is, you know, you're approaching t naught from the left, that's f of t naught minus, it has this value. You approach f of t naught from the right, it has this value, that's f of t naught plus. All right, there are two different values, it jumps, and if you look at the average of the jump, right in the middle, that's what it converges to. All right? Kind of cool. And this wasn't proved until I think the 1900s, sometime in the early part of the 1900s. So this was way after Fourier had done his initial work, and people were struggling with a lot of these problems. And this is useful enough that it comes up in application. So, for example, for the sawtooth, or not the sawtooth, for the switch periodic signal here, if it jumps from 0 to 1, then at a value of discontinuity converges to 1/2. All right? So you even sometimes see people define this function to be 1 on the interval from 0 to 1/2, leaving out 1/2, 1/2 at the discontinuity, and 0 from here to here. Right? You sometimes see that definition given, and the reason why people sometimes give that definition is because they want to anticipate this result. So if they want to use Fourier series, they say that it's sort of consistent with the definition of the function and consistent with the property of the convergence of the Fourier series. This is not so easy to prove. All right? None of these things are really easy to prove. It requires a lot of work. It requires a lot of estimates and careful analysis. But it's nice. It's very satisfying in some sense that it tells you, at least you know what the situation is. I'm not saying it's easy to establish, but at least you know what the facts are. All right? That's good. That's good. Okay? So any questions on that? This should be sort of part of your vocabulary. Yeah?
Continuity.
Then that's not a jump discontinuity. All right? What I mean by jump discontinuity, I mean it jumps between two finite values. Okay? Yeah, I'm trying to avoid, I'm talking to you in a somewhat informal way. I'm trying to avoid giving very precise definitions to all these things because you're going to see, you sort of know it when you see it. All right? You can do that, of course. You can give very precise statements here about the uniformity of approximation, about how it converges and so on, but that's not so crucial for us. It's just you should know, in general, what the big picture is. Yeah?
What about at other points? So if you have a function with jumps, so what about points where there are no jumps?
Sorry?
What about points where there are no jumps?
All right. What about points where there are no jumps? So actually, perhaps what I should have done is give a more careful statement of the continuous case. The more careful statement of the continuous case is the series converges at any point of continuity. All right. So if the function, if it doesn't jump, then if it's continuous at that point, then the series converges at that point. Okay. So that would actually be a more precise statement of it. Oh, I better not stop asking for questions here. All right. Because as I say, I'm trying to avoid the infinite regression of making the statements as precise as I can. I can do that, but you don't want to see that. All right. And again, don't underestimate the effort that it took to do this. All right. It was when Fourier first came out with his ideas, and we'll see his original application actually on Monday. He was very bold. He said that any function. He actually said any function, not just any periodic function, because he was thinking of extending a function to be periodic by just repeating it. You know, he was thinking of functions which die off and then repeating it. So he made statements like any function can be represented by such an infinite series, and people were scandalized by that. Especially they were French, and the French are easily scandalized. You know, c'est un scandale. You know, mon Dieu, any function, you are a fool, monsieur. You know, so it caused a great deal of consternation, and it caused a lot of work to get done to try to sort these things out. So don't underestimate the effort that went into getting even this much. But now, this was still ultimately not satisfying, because Fourier really set his sights very high, that any periodic phenomenon, never mind smoothness, you know, whatever, could be represented in some sense by a Fourier series, by this sort of infinite sum. And that took to sort that out and to get to the truth of that really required an entirely different perspective. So I wanted to say a little bit about that. I'll only get to it a little bit today, then I'll finish it up on Monday, and then we'll see some applications of this. All right? All right, so general case. That is not talking about continuity, not talking about smoothness, and so on. All right? And here what's really involved is we learned after decades, centuries of bitter experience, you need a different notion of convergence. Of the infinite series. You learned not to talk about what you think would be the most natural thing, point-wise convergence. All right? You learned by hard lessons. You learned it because it didn't work. I mean, ultimately, you couldn't get an answer that was very satisfying. In these cases, we're fine, but somehow under natural and fairly general situations, you learned not to ask for convergence of a sum like this. F hat of, let me just put general coefficients in there, c sub k e to the 2 pi I kt. I mean for general series, all right? You learn not to ask for convergence of that at particular points. At values of t. All right, you moved away from plugging in values of t and asking and looking at the series of constants and asking whether or not it converged. All right, and that was a hard step to take. Rather, what was ultimately learned was you get a satisfying answer if you ask for convergence in the mean, convergence on average. I mean, the proof that it was a good idea is because are the results that you can get if you take this point of view. And it was a hard-won point of view. So you get a better picture, more satisfying picture, if you ask for convergence in the average sense, or also sometimes called convergence in the mean, and I will write that down. Right? It's also sometimes called, in engineering terms, it's also sometimes called convergence in energy. You do see this term. For reasons which I'll explain, probably not today, but next time. Okay, remind me. All right, now what does that mean? Well, you need to make some assumption on the function. All right? It's not maybe completely general in the sense the function is arbitrary, but the assumption that you make on the function is pretty minimal. So again, I'm assuming the function is periodic. So really, everything takes place on the interval from 0 to 1. It's only the properties of the function on the interval from 0 to 1 that matter for us, because everything is just repeated after that. All right, so you suppose, again, f of t is periodic at period 1, periodic period 1. And you also suppose that it has the following property, that the integral, it's square integrable. Squared dt is finite. The integral of the square of f is finite on the interval. And that's not too hard a thing to insist on. It's not too restrictive a thing to insist on. There are functions that don't satisfy that. If a function goes off to infinity at a certain rate on the interval from 0 to 1, if it's unbounded, then it may not satisfy this. But certainly the functions that come up most often in applications are going to satisfy a condition like this. And this actually is sometimes the hypothesis of finite energy. For reasons which we'll understand a little bit more later, this integral is often taken to be the total energy of the function depending on what the function represents. And so you're assuming that somehow the signal has finite energy, which is a reasonable physical assumption. All right? Finite energy. All right. Then, as it turns out, then you can form, the Fourier coefficients do exist. That's something that actually has to be proved separately because it's a question of integrability, but it's true. You can form the coefficients f hat of k equals the integral from 0 to 1 e to the minus 2 pi I kt, as before, f of t dt. All right? Okay, so that's actually now a separate issue that has to be verified because you're not assuming the function is continuous or anything else. But it can be done. And the punchline is, and it's quite a punchline, that you still get convergence of the series, of the infinite Fourier series, but not, this board is floating up here, let me do it over here, but not by plugging in points, but rather in an average sense, as follows. So then, I'll write it like this. The integral from 0 to 1, I want to look at how close the function is to an approximating series. So that means a finite version of the sum. So the integral of the sum from k equals minus n to n of f hat of k e to the 2 pi I kt minus f of t squared dt. All right, so I look at the average of the square of the difference between an approximation, a finite approximation to the sum, makes perfect sense to form that, and the function. And the statement is that this tends to 0 as n tends to infinity. All right? The series converges to the function in the average sense. The series converges to the function in the mean. All right? The idea of integrating a function to get an average value is probably not so unfamiliar to you. One second. The idea of integrating the square or the difference of the squares is also probably more or less familiar to you. And as a matter of fact, this is exactly, again, for reasons I can't explain today, exactly related to the least squares approximation of a function by a combination of complex exponentials. Now, you had a question?
Is convergence in the mean square?
Pardon me?
Is this mean square convergence?
Yeah, mean square convergence. Thank you. I say convergence in the mean. Maybe I should even call it mean square convergence. If you're familiar with that term, by all means, use it. All right, so it's mean square convergence. All right, so the result is, and I'm afraid we have to quit for today, that the function, the series converges to the function, right? That is, it makes sense to write, you write f of t equals its Fourier series, k equals minus infinity to infinity, f hat of k e to the 2 pi I kt. But you have to understand what this equal sign means, all right, in this context. All right, in this context, you have to be careful here what this equal sign means. It doesn't mean plug the value of t and watch this series converge to the value of the function. It does not mean that. It means that if you compute that integral for a finite sum and let the degree go to infinity here, then that integral will tend to 0. The mean square difference will tend to 0. That's what that equal sign means. All right? That the difference between this and a finite approximation tends to 0 as the approximation gets better and better. The square. The integral of the square. Now, that was a big change of view. All right? That was a big change in attitude to adopt that notion of equality, that notion of convergence, and so on. And it had profound, far-reaching consequences. All right, and again, it took a long time to sort out. And we're out of time for today, so I can't tell you that. So on Monday, I want to wrap this up, only in the, not in all the mathematical details, only so far as to give you what the general picture is, because you're going to see it beyond this class. You're going to see people use this terminology, use these ideas well beyond what we do in here. And it's really quite satisfying. It's a really quite thorough and satisfying, coherent picture. All right, so more on that on Monday.